So we'll be talking about the rational method, and just as I was saying, the same method, the same design methodology is what you use, whether you are doing for SEWER, anything SEWER, whether it's for storm SEWER or for foul SEWER, right? It's the same thing. So if you look at this catchment, let's assume that this is a catchment that is about 75 hectares. It's a regular catchment, but in real life, you're not going to get it this way. It will be somewhat irregular. So this is catchment A, this is catchment B, this is catchment C, this is catchment D, this is catchment E. So it is regular, but in real life, it might not be that regular. So catchment H is the last catchment before the outfall. So our first assumption is that this place is a fixed boundary. In other words, every storm event that is coming here is flowing symmetrically to the outfall at catchment H. So once there is a storm event here in catchment A, it will flow into catchment B. The one for catchment B, C, will flow to catchment B also. Then together, they will flow into catchment D. Then the one from catchment E will join them at catchment F, while the one from catchment G will now finally join them at catchment H. So that is the progression. So whether it's for SEWER that's come from household or it's from storm that's come from weather events, storm events. So this is what the data we have for this catchment. These are the conduits. This is the beginning. This is the end. This is the length of each pipe. This is the slope. And then this is the catchment area bordering that particular catchment. So let me go back. This is the conduit for catchment that will conduct water, all the water falling in catchment A. This is the one conducting water from the catchment C, and so on and so on. So the conduits will bear the same name as the catchment. So if I say this is conduit A, it's also, why this is catchment A, this dotted line will not be catchment A. So it's the same thing. So when you start, you come up with a chart like this, a calculation sheet like this. You list them. How do you get these conduits? Well, it's from the surveyor's data, the beginning and the end of every node. So this is it. So you can say A, conduit B. It could also be A to B, B to C, C to D, like we did in water reticulation. So now, the first thing you do is you characterize that catchment. So let's start with the stormwater. In stormwater, last week we discussed about coefficient of peak runoff coefficient. We discussed it. We said that the area that contributes to runoff is the impermeable area. It is the only impermeable area that constitutes runoff. Either you call it impermeable or you call it paved. Call it paved area, or some people call it a contributive area. Other people call it the effective area. It all means the same thing. So if you look at this catchment, for instance, now, I call it catchment characterization. You characterize it. What does it constitute? Gardens and park made up 63% of this catchment we are trying to use. So this could be like more of a low density catchment. Let me put it that way. Good. Then the streets, if you categorize if you analyze the catchment, you will find out that the streets is made up of 2%. And for streets, let's assume it's an asphaltic pavement. The coefficient of runoff is 0.9, which is almost 1. Why? The coefficient of runoff for gardens and park, right, is 0.1. Last week I explained that this 0.1, of course, which is 10% peak runoff, even though we don't like calling it that way, using percentage, means that only 10% of storm will flow on the surface. So if there's a storm event, the runoff generated will only be 10% of the total amount of discharge on that catchment. I think it makes a lot of sense. The roofs constitute only 20% of the catchment, and the roof has a runoff coefficient of 0.95. Then others that we can't account for, maybe interlock area, working area, or what have you, is made up of only 5%. And the catchment, the coefficient of runoff is only 0.5%. So if you calculate 63, 12, 25, it will give you 100%. That is the entire catchment area. And these are the individual peak runoff coefficients. So how do you get this peak runoff coefficient, engineers? Simply, anytime you need to do it, simply go to Google or go to textbooks. You just say peak runoff coefficient of different bodies. All right. So it will just, if you go to images, for instance, it will give you the runoff coefficient of different surfaces. So let me go down. So if I go down now, look like this page now, right? Or like here now. So you can try it if you're in your laptop. You will see here it's telling you lounge is 0.05 to 10%. Heavy sandy soil, this. Residential areas, 0.3 to 0.5%. Industry area, light area, this. So agriculture area, and so on and so forth. So you can see thousands of them. So this one is giving you for road. Look at road. It's a paved road. It's 0.7 to 0.9. It's a permeable road, permeable pavement. I'm just wondering which one is permeable pavement. It will be 0.3 to 0.4. I think permeable pavement is things like interlock. When you put interlock, there are spaces. So it's not like 100% sealed, and so on and so forth. Then this is gravel road. Gravel road is 0.3 to 0.7. Then, I mean, you can just go on and go on. So it will give you all the values of the peak runoff coefficient. So this is our wetlands, just name it. So these are things you can just go online and you can get them. And look at bricks is 0.7, high one is 0.85, asphalt is between 0.7 and 0.95, concrete is between 0.7 and 0. And so on and so forth. So that's how we came about that. So if you go to the standard, rules are standard, it will also be there. So now this is what we need to do, because our major parameter for the storm event is to get what is the runoff coefficient. That is just it. Then on the other hand, for the sewer, we also have to get some parameters. For instance, you need to choose your design storm, right? And as a rule of thumb, you choose between 10 minutes and 15 minutes. In the course of the training, I will explain why you should choose 10 to 15 minutes, because that is when it's expected that the flow time and the storm time are the same. And it's at that point that you have maximum storm. You know, in our design as engineers, we're always designing against worst case scenario. So your question would be, at what point do we have the highest rainfall? Let me use that word. Or at what point do we have the most intensive rainfall? So from experience, from analysis, from studies, it is the first 15 minutes, not more than that. You can Google it in online. Then, if you are talking about the storm for the sewer, you now have to say, what is the land use? In other words, now it's a virgin land or it's a virgin area. There are no houses. If there are houses, you can now begin to estimate the population equivalent. But because you don't have the design, the layout, but we know the land use, we know that this is a medium density area, this is a high density area, this is a low density area, you can use that to parameterize your input. So in this case, we are assuming a land use of 100 capita a hectare. This is more like a low land use area, because what it means to say is that for every 1 hectare, I expect to have 100 people. I mean, 1 hectare is about 10,000 square meters. So that means if I assume 1,000 square meter is one plot, we're talking about 10 people in 1,000 square meter. That's what it means. Then, as I said, while I was coming, I was saying earlier that you use your water consumption as the input parameter for your sewage discharge. I want that to sink. The water consumption is just a way to is the value that you use to estimate the amount of wastewater that you produce. So in other words, it's like a law of continuity. What you drink is what you produce. So we are drinking 130 liters per capita per day. All of us we all know all these things. Then we now also come up with a peak factor. This time around, we don't call it runoff coefficient because we are dealing with SEWER, so which is equivalent, which is almost like opposite of drinking water, right? We assume a peak factor of 2. Then we also assume some parasite water, which I explained last time. Then, as with every pipe, you have to understand or know the roughness coefficient of the pipe material you are going to use. So, how do you determine the choice of your parameter, your size of your pipe? Of course, we've said it before. The sizing of pipes depends on the discharge it is conveying. It also depends on the slope of the ground or the slope at which you're going to lay it. Then finally, it also depends on the roughness. The rougher the pipe, the larger the dimension you need. Concrete pipe are the roughest, depending on the level of finish. Ductile iron are the medium. While PVC pipes are the least in terms of coefficient of friction. Then, the next thing is how do you determine your discharge? You determine your discharge by considering the wet weather flow, which is actually the dry weather flow plus the storm flow. Well, this formula is actually for the combined system, because if it's for separate system, which I have discussed, the dry weather flow is the flow for the SEWER, while the storm water flow is the flow for the storm. So, for the dry weather flow, please pay attention here now. We are still estimating how to determine the flow for both SEWER and storm. So when I say dry weather flow, it's as good as SEWER flow. And what is dry weather flow? It is that flow when there is no rainfall, when there is no storm event. The normal flow in your sewage network, when there is no storm event, is called dry weather flow. And that is the actual flow you use to size your SEWER network. So what does it comprise of? I want you to look at that formula very well. The first thing is your water demand, which is W_D. That's the water demand. So the water demand is 130. The second thing is the population equivalent, PD. The third one there is the factor of safety, which is the normal factor of safety. The fourth one is that parasite water. This parasite water, I've discussed it last time. No matter how impermeable your pipe is, there's always this sum of water that will come into your SEWER network. There's always this amount of water that will come into your, so you need to factor in some parasite water. I also want to liken the parasite water as, no matter the amount of water water board gives you, some people still buy bottled water, pure water, and all the what have you to make up for. Some people also harvest rainwater. So I want you to see that as part of the what do you call it? parasite water. So here, we assume 130 as our water demand. Then, after that, we now assume 100, the population equivalent to be 100 liters per capita per hectare, right? Then this 86,400 is the conversion factor. Remember that this is liters per day. So if we need to convert it to liters per second per hectare, we need to divide by 86,400. We multiply by 2, and then add it to the infiltration water or the parasite water as an additional factor of, as a second tier factor of safety. So at the end of the day, this is now the flow of wastewater coming from 1 hectare, because we are doing based on a spatial parameter. We are doing based on land use. So it means in this land use, this particular land use, for every 1 hectare per second, we're going to have 0.4 liters of wastewater coming out from these 100 persons. That's what it means. Because we don't know how many people we're going to design for. So once we get the parameter, the value of 1 hectare, we now multiply by the total number of hectares based on the attachments. We'll soon get there. Then for the storm, this is just the rainfall intensity, which is a function of duration and frequency multiplied by the area impervious. Did you get it? Multiplied by the area impervious. So that is that. Then, if you split it further, how do you get the area impervious? The area impervious is your catchment subcatchment multiplied by the corresponding average peak runoff. Assuming that it's so, if like in case of Abuja, you cannot say central area and Wuse Zone, Wuse 2 and Garki are the same catchment. They could be, even if they are, but you cannot say Kuje is the same or Nyanya is the same. Those ones might have maybe more of agricultural area, maybe more of green areas. Whereas Garki and Wuse, Ikoyi, Lekki phase 1, and so on, we have more of paved areas, meaning they might have different runoff coefficients. So all you need to do for you to get the effective area or the contributing area, you multiply the total catchment area, subcatchment area, by the peak runoff coefficient. That will now give you the effective area contributing this runoff. Please, any question on that? This is very important that you grab it. Good. Now, the other thing is that if you want to get your peak runoff coefficient, you use what we call mean weighted average. Mean weighted average. Just like we have here. If all these catchments are different, you can't just say that the average catchment now is this plus this plus this plus this divided by 5, divided by 4. You will fail it. You have to do what we call mean weighted average. And that mean weighted average is that you must take into consideration the constituent percentage. So in other words, if I come here now, I will say this multiplied by this, plus this multiplied by this, plus this multiplied by this, plus this multiplied by this, all divided by 100. It will give me something close to the real mean. Remember that mean and average have limitation because they don't capture the, how do they call it again? The internal characteristic of the variable. I think there's something like that. So for the mean weighted average, we'll now take those things into consideration. It will get you. So if you do the mean weighted average of these coefficients, you will get 0.37. But if you do the weighted average, if you do the mean average, the normal average, you're going to get like 0.5. But if you do the mean weighted average, you get like 0.37. And 0.37 is a better parameter to use. It's a better parameter to use because it captures more closely what is needed. So here now, for the storm flow, maximum storm flow will be the multiply 3 of them together. But however, if you have to choose your duration and frequency, what informs your decision? In the code and standard, depending on the risk level of your design or the area you're designing, or the mitigation extent you want to go. If you are designing for rural areas, you use 1 year return period. If you are designing for surcharge, 2 years. But if you are designing for flooding, you use 10 years. If you place a residential area, you are advised to use 2 years return period. But if there's going to be surcharge, you use 3%, 3 years. If it is now you are designing against flooding, which is the highest level of design in terms of safety, you use 20. If it's city center, you use 2 or 5 for surcharge and 50 for same. Underground railway, flooding, you use 50 years. Design storm, you use 10 years. Can someone tell me why you use 10 years for underground railway? Because if it floods, it is a catastrophe. Even in developed countries, you must do everything in your powers to make sure that underground railway doesn't flood. If it floods, the losses you incur will be in billions. Because everything under there will just submerge, and I mean, you don't have the sun or the free air going inside there to clean everything at that time. That's very important for us to understand. So this is what the typical IDF looks like. I think I tried to introduce it last week. And for the video I sent us, I think we treated IDF in intensity, duration, frequency curve. It treated it very well. So what I want to add here is this. If you look at this very well, you find out that this is just like the same thing we've been talking about. So this chart is trying to tell you that why is it that at the end of the day, not all the catchment contribute to runoff, rather a small percentage like this, which is gotten using the peak. So it is because you have drifting, you have evaporation, you have depression storage, you have infiltration, you have wetting. You have maintenance that takes place before the small runoff comes out. Then, I think that is that. Then you say additional delay due to travel time at the surface. We'll discuss travel time later. Then for the slope also, remember we talked about slope and the duration. The slope is affected, the duration of rain is also affected by the slope. If the place is less slow, if the slope is less than 1%, you are advised to use 15 or 20, 15 minutes rain. If the place is on a slope of 1 to 4%, you are advised to use 10 minutes. If the place is less than 4%, and depending on whether it's greater or less than 50% of the catchment area, you use 5 or 10. But I can tell you, please, you can ignore all these ones and use 50. That's the one that is more opinion. So if you go to the chart and read off this frequency duration curve, you're going to get 126 from let's just assume this. So let's assume that this is 156, which is the R. At 10 years, return period of 1. Get this. He said, but if flow time is longer than 10 minutes, only part of the catchment contribute runoff. So I don't want to confuse you with this. What this means is that flow time is important. How long will it take the water to flow from the beginning of the catchment to the area of concern or to the outfall? So how do you do your design? Number one, you choose your return frequency. That's the first thing you do. The next thing you do is estimate time of flow. Please, this time of flow is simply distance over time. Remember our velocity. Velocity formula is distance over time. So if you make time the equation of the formula, it's distance over velocity. And that's why it's important. Number 3 says, consult IDF curves for corresponding rate intensity. So the IDF curve will give you the IDF curve will give you an idea of the amount of rainfall. Okay, so that is that. So the next thing, you calculate the wet water flow or dry water flow, as the case may be. Then the next thing you do is you choose adequate pipe diameter. Consider security factor. So the required diameter depends on the roughness, the discharge. So that is that. So number 6, after you've done this thing, you can now go and consult the table to get a real velocity. I tell people that this is for academic purposes. Nobody will tell me the velocity of a place. In fact, to do the first one, you need to assume the velocity of 2 meters per second. So here, it talks about partly filled circular pipes. I'll discuss this partly filled at length and later on. Same thing applies to velocity. So number 7, you calculate the flow time, you compare your results, and then you do iteration if necessary. So we're back to that attachment. I think I've explained this before, right? I've explained this before. For the wastewater, this is the pipe number A. This is the beginning node. This is the end node. The corresponding catch area where that pipe is passing is 15.63 hectares. And if you now want to get the flow, the subcatchment flow, you multiply this by the amount of wastewater coming out from 1 hectare, which we have already gotten as 0.401. Here, this is where we do the calculation. So this is the amount of discharge coming out in 1 hectare. So when I now come to this hectare that is 15 point something, I'll simply multiply both. So here, I will now multiply 0.401 multiplied by 15.63. Somebody will ask, how did we get this? Let me write it. So the discharge from one catchment is 0.401. While the area of the catchment is 15.63. So common sense will tell me that the total amount of water coming from that catchment will now be the value of 1. Right? If you multiply these two, you're going to get 6 point something. Okay. So you can see, if you multiply it, you get this. If you multiply this area by 0.401, you get this. You multiply this, you get this. The next thing you now do is you aggregate, which is what we've done in the last 3 weeks. So if you look at this, you see that catchment A is flowing into catchment B. Catchment C is flowing into catchment B. So here now, as you're working from A to B to C to D to the last H, this is A. A flows into B. So here, 6.26 plus 2.19 will give you 8.46.
Hello.
Your screen is blank.
You can't see anything.
Okay, I was still on a. Thank you. So when you now come here now, you see that catchment A, the wastewater from catchment A will flow into catchment B on its way to the treatment plant located at catchment H here. So this is A. So to get B, you now say A plus B to give you B. A plus B to give you B. Are we together? So this last column means summation. You now sum it up just like we did. This one is 6. This one will now be this plus this will give you this. Catchment C is on its own. So it doesn't have any upstream. So you just simply continue. So this is how you'll be doing it until you do for all of them. So I'll quickly take you to a chart that shows you all of them have been done. And that is called rational method chart. I don't know why, wait, I don't know why it's not here. Okay, rational method here. So this is the chart. So to do this work, you need to develop a chart like this. One minute, please. Ah. One minute, please. I don't know what this laptop is telling me now. Hold on, just stay with me. I need to understand what is happening. Good. So this, what I've just explained to you now is here. So you can see A here. So B becomes this plus this will give you B. C is on its own. So this multiplied by 0.401, which is the throttle flow, the wastewater flow, the water, will give you this. But when it comes to D, this is the hectare of D. If you multiply by 0.4, it will give you 1.57. But the accumulated for D would be the value of B plus the value of A. Please, I want you to grab this. This is the whole thing. The value of B plus the value of A, then plus its own value. So if you want to know how we got 15.66, it is this plus this plus this, give you this. When it comes to D, is this. When it comes to E, if you look at E very well, E is independent. It's an independent catchment. It does not have upstream. So it remains here. But F have the upstream of D, right? And E. So if you add this plus this, you get this. So this is how you'll be doing it for all of them until your flow will keep increasing from 6 to 8, then it reduces to 5. But on the main critical part, it will be increasing until it gets to 30 liters per second. So this is where wastewater will end. So after here now, you go to pipe size and size your pipe using the discharge, the slope, and the roughness. But if you want to continue with stormwater, then the next thing you do is now to say what is the runoff coefficient of all the catchments. So since catchment A to catchment H, we assume they have the same runoff coefficient.
Sorry, engineer.
Yes?
Hello?
I can hear you, sir.
Yeah, please, is it possible to share the two screens so that the two pages in the same screen so that we can read it side by side?
Okay, that would be near impossible, but let me try. That was why I used this one to demonstrate. So let me go back to this one again and demonstrate it with this one. And you open it on your screen and try to see if you see what they've done. It's almost impossible because I don't know. Just not how this goes. So now watch here now. This is A, catchment A is on its own. So the aggregation will be 6.26 as total wastewater flow. But when it gets to catchment B, this is the value for catchment B, 2.19, by virtue of its small catchment area. So, but the real value for B flowing in this B now will be the one for A plus the one for B. And that will give you. When it comes to catchment C, you can see that catchment C is just it's a beginning, it's just beginning. It does not have upstream. Why catchment B is big, while the catchment is small? It's because catchment B is the upstream. No, catchment B is the downstream of A. So A is on the upstream. So that is how you'll be working it through. So please bear with me on this small format. So try to relate all of them. Try to relate all of them, you see. For the storm, since we say that the peak runoff is homogeneous, so we just replicate it all through here. Then the area impervious, instead of multiplying, in the case of this one, we are multiplying this charge by the discharge per hectare. In this case, you'll be multiplying the peak runoff times the catchment area. So this one, this value, area impervious, will be 0.37 multiplied by 15.63. 0.37 multiplied by 4.47, 5.47. 0.37 multiplied by 14.06. 0.37 multiplied by 3. So this peak runoff coefficient is now helping you to reduce the area or to bring up the effective area for your runoff contribution. So when you multiply this by this, you're going to get this. And this is not the true area you're going to work with. So you now do the same thing you did here. You aggregate the areas. This is area A. But when it comes to B, it becomes this plus this. Now gives you B. When it comes to C, C is the same thing. When it comes to D, D becomes the value coming from C plus the value coming from B and the value of itself, making it 14.49. Is that understood? Okay. So when you put here now, you now aggregate it. One thing you know that you're getting it right is that as you are moving down towards the treatment plant or towards the last manhole or towards the intake of the treatment plant, you can see that the discharge is increasing from 5 to about 27. So the other things now are not relevant, but let me explain to you what they mean. This is the estimated time of flow. Estimated time of flow. This estimated time of flow is just like we said in our table. We said that the length of this pipe is 500. So if it's 500, you assume a velocity. That's what we do. Normally, we assume 2 meters per second as your velocity. But you can Google it and you find out the appropriate velocity to use based on your reference coefficient. So for the sake of design and for nominality, you just use 2. You assume that the water is flowing at the rate of 2 liters per second. So if the water is flowing at 2 liters per second, remember our velocity formula. Velocity is distance over time. If you divide the distance by the velocity to give you the time. And in this case, it's about 250. 250 seconds, if you convert it to minutes, is less than 10 minutes. So you use the value for 10 minutes. If you try to reduce it, you compare it. That we all do it in engineering. So this estimated time of travel, you can see it here is 250. How do I get it? 500, which is the length of the pipe, divided by the velocity. If you make it in the formula for velocity, distance over time, if you make that the average of the formula, you get distance over velocity. So you fix velocity, assume a velocity. So the idea of estimating this time of travel time is that if it is more than 10 minutes or less than 600 seconds, you use the value for 10. This might be complicated for some of us, but that is what it is. Estimated time of flow is a time when the water enters from one catchment, from one beginning of the catchment to the end of the catchment. So we are now saying that if that time duration is more than 10 minutes, if it's less than 10 minutes, use the value for 10 minutes. And that's why when you go to your IDF curve, you read off 10 minutes. You don't go read off 250 seconds. You won't see 250 seconds there. So if you now multiply the rainfall duration, if you now go to your IDF curve, you read off using the frequency and the duration of rain, you get your runoff value, which is 126 liters per second per hectare. You now multiply by the corresponding effective area. So to get this, you multiply this by effective area. Multiply the effective area here by this. Please, this first one, area impervious. Multiply by this rainfall intensity. You're going to get your rainfall discharge. In this case, 532.15. After you get this value, you now go to your charts or go to other tables that are everywhere in the internet. You now ask yourself, if my discharge is this at a particular runoff coefficient, roughness factor, what would be the pipe size? That is how you now get your pipe size. So that is that. So sometimes I don't want to go into all this. This is just gymnastic, right? You can do addition. If I want to estimate the time of flow between A and D, it means I'll add time of flow for A plus time of flow for B. Time it has to use flow. That will give me time of flow. This time of flow, that is why sometimes it's easy to predict flood. Once you estimate the time of flow of a flood event that happens at a distance of 100 meters, you can estimate the time of arrival in this place. Then you know what the value will be in this place. And then you know what mitigation strategy you should use, but let's not go into all that. So you can use rainfall table to read off your runoff, or you use charts. 1 means return period of 1 year, 2, 0.5, and so on and so forth. This is the interest table, sorry, the design chart. So once you do that, you get your value. After you got in your value, you now go to the chart and then size your pipe. I think that is all. So this is the concept of rational method. You can read and understand it, and you just have to move forward. So you could see this is 3 catchments: catchment A, catchment C, catchment B. So for catchment A, it is 4 hectares. But the peak of runoff is 0.4, right? And the maximum time is 10. B is even looking big, too long, right? And therefore, the maximum runoff time would be 5 minutes, and so on and so forth. And the reasons are self-explanatory. Is you understood? So for this instance now, the runoff coefficient here will now be the catchment area multiplied by the peak runoff coefficient, right? And if you look at it, it gives you 182. Then if you multiply 14 hectares by the peak runoff of 0.4, it will reduce it to this. Then multiply that with this, it will give you 662 liters per second. Any question? Any questions so far?
Good evening. I have a question.
Thank you.
My question is, you said this design is for SEWER and STORMWATER. Yes. So
yeah,
in an area where the water from the SEWER is not allowed to go into the storm, for example, until when it
doesn't go. Please, it doesn't go. It must not go, except for where you have combined system. And I said that 95% of the world are using separate system. Please take note. You cannot combine.
Sorry, hold on. Let me finish my question.
Okay.
Yes. In a situation whereby the water has to go through treatments, through the treatment plant, for example, before it comes into the storm, you know, you're still designing for boats. I feel that it's not economical to take the storm water to treatment first before bringing it to storm. What would be your suggestion? Because I'm thinking this design, I mean, from what we have at the moment, seeing the trend, it's not economical to actually combine it. The fact that government will not allow you to discharge sewer water into the storm water. So maybe you should clarify it. Then you were using some charts where those charts designed by you, or I can see one as a German reference. Can you refer us to the one in the Nigerian manual for use of adaptation? Thank you.
Okay. Thank you so much. That's a good question. Now, on no account must you discharge SEWER and storm together. What I said at the beginning of the class is that the 90% or 95% of the systems we have in the world is a separate SEWER, a separate storm. The SEWER is one we call gutter. The storm is one we call gutters, right? They usually discharge themselves into open bodies, open water bodies. If they are highly polluted, you use what we call combined SEWER overflow to hold them a while, so that the top decanted surface will flow to the river storm. The idea of you not discharging all these things is going to introduce shock on the aquatic life. So 95% of the time, it is not advisable to design a combined system. It's only in high-tech areas like New York, Manhattan, and all these cities that are already in want of space. So that is where you now see them. But in most cases, what people do is you put the SEWER at the bottommost, then you put the storm at up, right? The SEWER is always an enclosed pipe. The storm can be open drain. Most of the time it's open drain. Trapezoidal member, rectangular member. So please, it's good that we understand the distinction between these two. And in no account must you combine the two. It is not advisable, it is not ideal. It will lead to outbreak of diseases. Because when you empty those foul sewer into the open river body, you know what will happen. All sorts of diseases will prop up. So that is one. Then the second one is that all the codes I'm using for this training, with all due respect, these are German codes, which today have become Euro code. So our former British code standard we are using have already merged into Euro code. We're in order. The only thing we are yet to do is first customize it to become Nigerian thing. But if you go to that highway design manual, some of them are captured there. Right? I don't know if that answers your question, madam.
Yes, it does.
Good.
Okay.
So we have a code now we are using. It's called the Highway Design Manual. It's in volume 1, volume 2, volume 3, volume 4, volume 5. Volume 3 and 4 is where we have the one for storm. Now, I'm not conversant with the one for British standard, but I can bet you if you go to British standard, it's the same thing, no difference, because the British standards have metamorphosed into Euro standard. German DN standard have also metamorphosed into Euro standard. And we always leaning towards British is very, very okay for us to be using Euro code, which by extension will be in conformity with the old German code. For instance, we say that the drinking water requirement per capita per day is 130. Please, in Nigeria, do you think we should use anything more than that? No, it's better to be safe. I know that Abuja was designed with 100. I keep saying it all the time. So let's assume that extra 30 to be an increased factor, which of course will even lead to oversizing anyway, but which is in the direction of safety. Then if you are talking about safety factor, using a safety factor of 2 is the same thing. Talking about the rain duration of maybe 10 minutes, 15 minutes, or 20 minutes is almost the same thing. The same way it rains there is the same way it rains here. The first 15 minutes of every rain will determine the intensity of that rain. That's just the simple layman's interpretation of that. Very important, please. Okay, so that is all about catchment, about national method.
Hello, can you hear me?
Yes.
Yeah, when you mentioned that in the combined system, which according to you is about say 5% of the times in a high-tech institution, how do you I'm just trying to wrap my head around the way you want to separate the two of them, leaving the sewer or the processed water under. Is it that you are going to have a system where you have a layer, I mean, maybe a structure separating processed water from the stormwater, but they maybe let me assume you have one drainage system with a separating structure. Is that what you mean?
That is part of it, but not all. Number one is that when there is no storm event, the whole water will flow to the treatment plant. Once there is storm or it starts raining, you introduce what we call bypass structure to bypass some of the water into a temporary holding pond, right? Then what they do in the few places they have it, in fact, I use the word 5%, it might be 2% or 1% in the world, is that when there is normal dry water flow, the bypass structure, somebody is there operating it, either automated or manual operated. The person will bypass it. It will flow into the treatment plant for treatment. But once there is storm event, he will shut it down. Then the thing will be flowing into a holding body, which they call combined sewer overflow. It's more like a big tank, retention basin. Then when he retains it for like 2-3 days, the clear water will flow into the river. And then the sludge, right, or the suspended material will now flow back into the treatment plant. That is the only way I know they operate it. But this is so risky, and so you can't just practice everywhere. A couple of days back, I went to visit a dam, and I told them that here in Nigeria, we cannot use our spillways. We can't use automated spillways in Nigeria. We can't use gated spillways. In many countries, they have gated spillways. Once they see that the storm or the dam is, the water inflow into the dam is becoming too much, that they don't have enough freeboard, they will open it, the gated spillway, and water will flow out of the spillway. I told somebody, but in case of Nigeria, you don't even try it, because the person who is monitoring that will just go to farm, and the whole dam will be toppled. So if you watch all our dams in this country, we don't have gated spillway dams. It's almost impossible, because someone will just tell you there's no power to, the thing cannot open automatically, or the person, the may guide have gone to market or have gone to see his family, and then there's storm, and there's nobody to open the gate. So the same thing applies to these systems. These systems are systems where you have structure, where you have a dedicated somebody whose work day in, day out is to monitor when there's storm event and when there's no storm event. Okay.
Sorry, before you proceed,
okay.
Just being curious. I know that at times when you use a rational method for design is when you have a very huge catchment area, say above about 12 kilometers squared or thereabouts. So, but from what I can see, we are combining this also with a SEWER. Does it mean that we'll be expecting huge volume of water for SEWER that requires us to adopt rational methods for its design?
Okay, that's another good question. Now, the rational method is limited to 100 hectares. I want you to get that in. It's very important. Actually, rational method have limitation. Once the catchment exceeds 100 hectares, it gives you, it gives you error. Not like it gives you error, the output becomes becomes subjected to error. I will explain to you why that happens. Very simple. I want you to understand it. Once the catchment is bigger than 100 hectares, it's a spatial thing. Rational method, now the accuracy goes down. It's not that it is wrong, but the accuracy goes down. The reason is this. For you to get the effective flow, the time of flow must be equal to the duration of flow. The time of flow must be equal to the duration of rainfall. That's the point. And rational method is majorly applicable in stormwater. When you hear rational method, stormwater should come to your mind. But the same principle can be used to design your SEWER. Because at the end of the day, the discharge from SEWER is like 10% of the discharge from storm, or even 5%, or even 2%.
That's exactly why I'm asking the question.
Because sometimes that's what last week I told us that use PVC pipe for SEWER. It can be 4 inches, 5 inches, 6 inches, 7 inches, 8 inches. But storm can be 1.2 meters, 1.5 meters. I've seen 3 meters in Asaba. I keep saying it. 3 meters storm rectangular channel in Asaba. It's possible, depending on the huge flow that they're anticipating to flow into River Niger. So rational method is limited to 100 hectares because at that point, it is no more accurate. That does it. So what you do as engineer is you scale your factor of safety. If rational method now gives me 1.2 meter diameter pipe, me will increase it to 1.3 meter or 1.4 or even 1.5. But to something reasonable. Is that okay? Okay. Let's continue. So the last thing we'll do now is to look at what I've done the design. You know, instead of us doing it one by one, I've already done it, and I want to present you the result. And it's in your material. Catchment calculation for SEWER, catchment calculation for storm. So this is what it looks like. So we are using 130 liters per capita per day. The population is 100 per hectare. Parasite water is this. Then we've done this. We've done this. So For catchment A, this is the area. To get the discharge, we multiply the dry water flow. Remember, we're doing SEWER now, SEWER, right? File SEWER. Dry water flow multiplied by the population equivalent, multiplied by the safety factor, added this thing, we got this. All of us know this. So my job now is multiplying the discharge, because the discharge is the same for all the catchment. We assume it's a homogeneous catchment. So the SEWER will now be the discharge, which is per hectare, multiplied by the corresponding subcatchment area, also in hectare. So hectare will cancel hectare. You'll be left with 2.69 liters per second. With this, you go to your charts. I cannot teach chart again because I've got it in water rectification. So go to that nomogram and now read off what is equivalent of 6.29. But the rule for SEWER says that the minimum SEWER pipe you must use is 150 mm. Please take note of that. The minimum pipe size you must use for your infrastructure work is 150. Within the building, within the houses, you can use 4-inch pipe, which is 100 mm. But once you are going outside, once you are going to the streets, the minimum you use is 150. So irrespective of the volume you got, the size of pipe you got, 150 should be your minimum. That's what the code says. For me, I believe why they say so is that sometimes these things carry tissue, carry some rubbish, carry some dead animals and what have you. So even though 4 inches or 3 inches can convey that flow, but because of other contingency factors, because of other safety consideration, you're expected to use 150 mm pipe. So if you go to the charts, you read this against 5%, which is from the slope, you get 125 mm. But you will not use 125 mm, you use 150 mm. So that's what the code recommends. For catchment B, stay with me. This is the same thing. For the SEWER, you multiply by this, you got this. But the resulting aggregated flow will now be the one you got for A plus the one for B, that will give you 8.46. So by this, considering the slope of catchment B, which is 3% or 3 per mil, you now read it off against this. The answer will give 150 mm pipe. So for catchment, sorry, I'm trying to get my hands on this. Hold on. Okay. So I think I didn't do, or I just did 1 or 2. So here you will now continue with the remaining one. So for catchment D, the same thing. When I got catchment D as 1.457, I now have to go and add it to B, C, and D. So it becomes 1.57 plus the value for B plus the value for C, because C is already adjacent. The whole thing will come to 15.66. 15.66, the slope is 0.25. When I read it off, I'm getting 200 mm pipe. Catchment D, E is on its own. So when I go 5.95, the answer is 1.25 mm. So I use the normal nominal 150 mm. So, and so on and so forth. So if you do this, this is how you now get it. This is the pipe sizing now. You are getting the pipe sizes from your nomogram. After you finish, you move over to the storm and do exactly the same thing. The only difference is that when it comes to storm, you won't be getting all these 0.0 point again. Rather, you'll be getting bigger values. So if I go to storm 1, the one for storm, here. Please, I will be stopping the class in the next few minutes. But what I will do, I will send us the video. Please, instead of us spending the next 1 hour, just watch this video, and it's as good as we'll be together for the next 2 hours. So for the storm, exactly the same thing you will do. The difference is that when you get this area, you multiply by the peak runoff to get the effective area. Multiply the effective area from the value you read off from your IDF, you get this value. And when you get this value, you now go to the chart. When you read it off in the chart, you get 700 mm as the pipe for catchment A. Catchment B, 900 mm. So I'm going to leave this with us now and this video. By next week, we're going to review what we've done in the last 1 hour. Let me pause the recording.